All right, today we're in section 14.6, scientific notation. So, again, we're still going with the no calculators. All right, you don't need them really, especially for these sections for scientific notation, because especially in 14.6, you're not actually solving for anything. Okay, you're basically rewriting really, really big or really, really small numbers in a shortened way, and then you're kind of working in and vice versa as well. Okay, so just some important information that you need to know to kind of start off this unit. Scientific notation is a shortcut. Notice, shortcut. You're not solving anything. Okay, so scientific notation is a shortcut for writing really big and really small numbers. Okay, you use powers of 10 with scientific notation. So you're always going to see 10 as the base. You're multiplying by 10 to a power, all right, whether it's positive or negative. All right, and then standard form is the expanded. That's the really, really big numbers that we see. And then scientific notation is the shortened version. And you always have a decimal value between 1 and 10. All right, so can anybody give me an example of a number between 1 and 10 that has a decimal value with it? Give me any number. 5.2. Okay, so let's go with 5.2. Okay, 5.2. Somebody give me another one. 8.3. 1.0. Yeah, it's about as close as it gets. Okay, could I say 2.6543?
Yes.
Okay, so I'm getting a bunch of numbers after the decimal, but it's still in the correct range. Could I say 0.68?
No.
No, that one doesn't work. Could I say 3.24?
Yes.
I said a 2, but I wrote a 3. Okay. All right. Yes, 3.34. Yes, that could work. What about 12.6? No, because it's greater than 10. So I'm looking for decimal values in these really large numbers. I need to move the decimal to a place that gives me a number within that range. All right, so let's look at example 1. In the top two numbers, I see they are really big numbers, right? They're very large numbers. All right, so what I'm going to do is I must move my decimal point. Wait a second. To move my decimal point, I have to have a decimal point.
It's at the end. It's at the end.
Okay, so we all understand if there is no decimal in the original problem. All right, so when there's no decimal point in the number, we know that it's understood to be after the ones place. Okay, you don't necessarily have to write that in, but that's where it is. Okay, so what I'm doing is I am moving it after the first non-zero digit in the number from left to right. And when that happens, it automatically puts the number in the correct range. So I keep moving it, keep moving it, keep moving it after the first number that is not a 0. And now that number is in the correct range. Does everybody agree 1.73 is greater than 1 but less than 10? Okay, so if I had put it after the 3, well, 173 is way too big. Okay, so now here's what I do. I always multiply it by 10, but now what is my exponent going to be? Okay, it's going to be however many place values are between the old and the new decimal place. So I have 3, 6, 7, 8. 10 to the 8th power. Okay, it's not how many zeros are in the number. It's how many place values are between the old and the new decimal places. Okay, and that's my final answer. All right, that's my answer. 1.73 times 10 to the 8th power. That's how I could write this very large number in scientific notation. All right, so now I want you to do the next one over. 25 billion. Okay, go ahead and write that number in scientific notation. So someone give me the decimal value. Isaiah? 2.5. Did everybody get 2.5? Yeah. Times 10 to the what power? To the 10th power. Okay, again, because the original decimal was here, I go 3, 6, 9, 10 to get to the new place. I went 10 place values to get to the new place. You don't have to draw that arrow underneath the number. You can if you want, but you don't have to. 10 to the 10th power. Okay, did you guys get that?
Yes.
So if my exponents are positive when I'm writing really big numbers in scientific notation, what do you think is going to be true about your exponent for really small numbers? It's going to be negative. Okay? So you're still counting place values, but now you're going in the opposite direction. But you still need a decimal value greater than 1 and less than 10. Okay? So again, we're just going to go left to right until we get to the first number that is not 0. 3. So that's where my decimal is going to go. 3.2 times 10, and I count how many place values I moved my decimal. 3, 4, 5, 6. 10 to the negative 6th power. Don't forget the negative, guys. Okay, even on the end of course exam that the 8th graders just took, I still was revisiting this topic with them. They're forgetting that it's negative when it's a really small number. All right, go ahead and try the last one. Go ahead and try the last one, and we'll go over it. Okay, Noah, what did you put for your decimal value on that one?
5.007.
Okay, 5.007. Normally, we don't have to put zeros in our decimal value unless it's acting as a placeholder. And here, if I drop my zeros off, then it's going to look like 5.7, or I will not even have a 7, and so it changes the value of the number. So I have to have my zeros times 10. And Kiana, what did you put for your exponent on that one?
-4.
Yes, it's going to be -4. Did you guys get -4?
Yes.
10 to the negative 4th power. All right, so writing in scientific notation. That's the first section on your homework tonight. Is just writing these numbers in scientific notation. All right, next example deals with writing numbers in standard form. So now they're already in scientific notation, and now I'm going to put them back into standard form. The exponent tells me everything I need to know about how this number is expanding. If the exponent is positive, I'm moving my decimal to the right. I'm making the number bigger. So what do you think is going to happen to my decimal if the exponent's negative? It's going to move to the left. It's going to make the number smaller by that many, hear me on this, place values, not zeros, okay? So let's look at the first one, 3.22 times 10 to the 5th. The 5 tells me I'm expanding by 5 decimal places. But how many decimal places, and remember, because it's positive, I'm going right. How many decimal places are already in the number? 2. So how many more zeros do I need to make 5?
3.
3 more zeros. So here's how I want you to do this. I want you to write the number. Do not put your commas in until you write all of the digits. Okay? So we're going to go 322 and 3 more zeros. And then I'm going to work back from right to left to put in my commas and box in my answer. Okay? Because what will happen is you write the first 3 digits and you try to put a comma, but then on the back side that doesn't work out so well. You have like one random digit at the end. Okay? So write out all your numbers and then go back and put your commas in. Okay? All right, try the next one down. 4 times 10 to the 6th power. 4 times 10 to the 6th power. You have to decide how many zeros am I going to add after the 4, okay? And then go back and put your commas in. Let's see, Aramis, how many zeros did you put in after the 4? He put in 6 because there's no decimal values that would count as some of those, right? There's no decimal value in 4, it's just 4, okay? Or you can say 4.0. All right, so I add in 6 zeros. 1, 2, 3, 4, 5, and 6. And then go back and put your commas in. All right, did you get that right? Raise your hand if you got that right. 4 million? Okay, good. All right, guys, so now let's look at the negatives. So if you're adding in your zeros after the number for a positive exponent, where do you think your zeros are going to go for the negative exponent? They're going to go in front of the number. What you're doing, though, you have to understand what you're doing. You're moving your decimal, your original decimal. So it's not going to be in the original place. You're actually moving it out. Okay? So we have 7.9 times 10 to the negative third power. All right? So we just said, which way are we moving our decimal?
Left.
To the left. Okay? So guess which one counts? The 7. That counts as 1 because I'm moving it left. Everybody got that? So how many more zeros do you need in front of the 7 to take it out 3 place values? 2 more zeros. Okay? So it's going to be, now the first 0 doesn't count because that's just my placeholder. 0, 0, 7, 9. All right? What I want you to see here is, does everybody agree that this is where the original one was, between the 7 and the 9? There are 3 places between that should match the exponent. All right? This is how some of my students have written their answer in the past, though. What did they miss? What did they do wrong?
You can't take out the decimal.
They didn't understand. What I'm actually doing here is I'm moving this decimal to a new location. It's gone now. You can't have 2 decimal places in one, or 2 decimals in one number either. Okay, this is my new answer. You got it? All right, I want you to try the last one. Okay, Morgan, how many zeros did you put in front of the 8?
I added 5 zeros to the
Very good, 5 zeros. Because the 8 counted as 1 place value and I was moving to the left. So 4, 5. And did you include, guys, the entire decimal value?
Yes.
All right, so I had some dropping it off after the 8 and they didn't put the 334. If you do that, you're changing the value of the number. You can't do that. Okay? So this is going to be my answer. It's a really long number. It's the expanded version of that number. All right, one more example. We need to talk about measuring. Guys, this is so obvious. Can we just kind of go through this together? It's pretty obvious. Okay, a foot. Which one does that match with? And I think it's fill in the blank on your notes. Just tell me, which one does a foot match with? Yeah, and wait, hold on. The height of an adult. Yes, the height of an adult. All right, what about liter? What about liter?
Soft drinks.
Buying soft drinks. Yes. What about milliliter? Okay, yeah, mosquitoes. And what about inch? The baby, the infant. And mile.
Oh, this is in Jacksonville.
Yeah, Jacksonville, Orlando. So why are we even doing this? Well, when you're given a real life problem, okay, so let's say, you're a police detective and you're at the, scene of a crime and you're investigating and you're trying to figure out from, or maybe a scene of a car accident. Okay, maybe we'll scale it back a little bit. Car accident. How far apart the cars were from each other. Okay, and you go up to your reporting officer and you say, they were approximately 2,300 inches apart. What do you think the officer is going to say to you? What in the world does that mean? I want it in what? Feet. Because of the scenario that, we're talking about, right? Okay, so depending on what scenario you're given, a modeling real life question will depend on what unit in your answer is actually appropriate. Does that make sense?
Yeah.
So that's kind of why we put this slide in here in the first place. Because now we're going to go to example 3. Well, it says a female flea consumes about 1.4 times 10 to the negative 4th liters of blood per day. So imagine a mosquito. Is it practical to express this in liters? No. So why did they do it in the first place? To make your life miserable? No. Okay, because they needed a number and scientific notation to tie in with the lesson. Okay? So we're going to go with it. All right? Well, if that's 1 and a dog has 100 fleas. Poor doggy. I know. Okay? What is the total amount of blood that those 100 fleas are taking off of this poor dog each day? Okay, so here's what you need to do first, and what I need you to do on your paper, and you know how to do based on the previous examples. Write this number in standard form. This is how you will do number 30. You're going to write this number in standard form. Okay, so in standard form, all right, say it with me. It's 0.00014, okay? But that's just one. How many do I need to calculate? 100. So I'm going to multiply this by 100, okay? To figure out, well, that's 1, but I multiply by 100. And what happens when I multiply a number by 100? What happens to the decimal? It moves to the right because you're making it bigger. So it goes 2 places to the right. So this is 0.014 liters. This is my answer. However, it goes back to the police example. Would that be practical for me to report this to some scientist? 14 thousandths of a liter? Maybe, maybe not. Probably not. Okay? So instead, I can convert this to milliliters. Milliliters. To go from a really big number. Okay, so I do a hand motion, and sadly this doesn't show on the video. To go from a big unit to a small unit, I multiply by that many. Big to small, you multiply. You see how that kind of works? Small to big, you divide or something. I don't know. It's like hands out, okay? All right, so you kind of cross your arms. Hopefully that helps, okay? So to multiply this by 1,000 would move the decimal how many more places to the right? 3. So 14 thousandths of a liter is the same thing as 14 milliliters. Okay? Which is a more practical answer to this problem. Okay? All right. So that's how you're going to do. So on 30, this is like 30A right here. And then 30B involves some conversion. Okay, so that's kind of very similar to number 30. All right, and we should be good to go. After that, let's go ahead and get started on our homework.